Day 765 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 2196, create binary tree from descriptions. The difficulty level is medium, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, hype, subscribe, comment, and share. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. You're given a 2D integer array descriptions where descriptions of I is equal to parent I, child I is left I. Indicates that parent I is the parent of child I in a binary tree of unique values. Furthermore, if is left I equals 1, then child I is the left child of parent I. If is left I is equal to 0, then child I is the right child of parent I. Construct the binary tree described by descriptions and return its root. The test cases will be generated such that the binary tree is valid. All right, y'all, so that may seem a little bit confusing at first, so let's go ahead and take a look at these examples just to make sure that we are doing this problem correctly. So, in example 1, we have our input descriptions equals a 2D array of integers. First array is 2015 1, the next array is 2017 0, then 50 20 and 1, then 50 80 and 0, then 80 19 and 1. The output is this binary tree that they give us right here, or an array of integers 50 20 80 15 17 19. Boom. The explanation says the root is the node with the value 50 since it has no parent. The resulting binary tree is shown in the diagram. So let's break this down one step further, right? So we know that descriptions of I, that's going to be each array in the 2D array. So this is descriptions of I, this is description of I plus 1, this could be descriptions of I plus 2, and so on and so on. Or they all could be descriptions of I as we iterate through it. Either way, I'm getting off track. So now that we know the descriptions of I, each array has 3 numbers, right? A parent, a child, and its left. So this number represents the parent, this number represents the child, and this number represents its left. If this last number is 1, then it's the left child of a parent. If this last number is 0, then it's the right child of the parent. Now, let's keep going because we're not done yet. As you can see, we have this 20 right here. That means it's the parent. So this 15 is the child of 20, as you can see. This 1 right here lets us know that it is the left child of 20, as opposed to when we move right here, we also have 20 is the parent of 17, and the 0 lets us know that 17 is the right child of 20, right? So that's how we know what this looks like right here. Boom. Notice it says the root node is the node with the value of 50 since it has no parent. So you notice that in all of these arrays, 50 is never the second number. That means 50 is never the child. That means it has to be the root node, right? Because it's only appears as a parent. It's the parent of the 20 right here, and 20 goes to the left. 20 is the left child. So 50, 20 is the left child of 50 on the left. Boom. Then 50 is also the parent of 80. Boom, and this 0 right here lets us know that it is the right 80 is the right child of 50. Boom. Then same right here, 80 is the parent of 19, and this 1 right here lets us know that it is the left side of 80, that this 19 goes on the left side of 80. Now, just in case that didn't make sense, y'all, let's take a look at example 2. So in example 2, we have our input descriptions equals a 2D array of integers 1 2 1. The next array is 2 3 0, and the last array is 3 4 1. The output is 1 2 0 0 3 4, or that's a binary tree or an array of integers 1 2 0 0 3 4. So let's go through it. It says the root node is the value 1 since it has no parent. The resulting binary tree is shown. So like I showed you before, 1 is the root node, similar to how 50 was up here. Boom. And we know that 1 is the parent of 2, right? And 2 goes to the left of 1. So boom, we put the 2 on the left of 1. Then we keep going. We know 2 is the parent of 3. So, and then 3 goes to the right of 2. So 2, parent of 3 to the right. Boom. Then we know that 3 is the parent of 4, and we know that is the left child. So once again, this 4 goes to the left, and that is how we got this binary tree from this 2D array of descriptions right here. Boom, y'all. So now that we understand the question, let's get into the fun part, the actual solution. The solution is not that difficult at all. Now, the first thing we're going to do is we're going to create a dictionary that will map a node value to its corresponding tree node object, and this will allow us to reuse existing nodes instead of creating duplicates when the same value appears multiple times. So we'll just come right here. We will declare a variable called nodes, colon, it's going to be a 2D array, or not, excuse me, not a 2D array integer. It's going to be a dictionary with the key is going to be an integer, the value is going to be a tree node, and then we'll initialize it with a blank dictionary like this. Boom. Come underneath that. Then we need to store all of the values that appear as children, and later this will help us identify the root node. So we'll declare a variable called children, say colon, it's going to be a set of integers, so set less than int greater than, and we'll initialize this with a blank array. Boom. Now we need to process each parent-child relationship. So we're going to say for DESC in description, we're going to open up the bracket and we're going to extract parent node values, child node values, and whether the child should be attached to the right or left side by saying let, open up the parentheses, we're going to say parent val, comma, child val, comma, is left equals, open up the parentheses, DESC square bracket 0, come outside of that, comma, DESC square bracket 1, come outside of that, comma, DESC square bracket 2, come outside of that, we say equals 1. Boom. Now we need to retrieve the parent node if it already exists. Otherwise, we're going to create a new tree node. So we'll come underneath this. Sorry, y'all, not underneath this. Oh, yeah, underneath that, still inside the for loop. And we are going to say let parent equal nodes square bracket parent val. Come outside of that, question mark, tree node, open up the parentheses, pass in parent val. Boom. Then we're going to do the same thing for child and retrieve the child node if it already exists. Otherwise, we'll create a new tree node. So come underneath this, we'll say let child equal nodes square bracket children val. Oh, excuse me, not children val, but child val. From right here, square bracket child val. Come outside of that, question mark tree node. Open up the parentheses, pass in child val. Boom. Now we need to attach the child we need to attach the child to the correct side of the parent. So we're going to come underneath this and we're going to say if is left. We're going to open up the brackets and we'll say parent dot left equals parent. Or excuse me, equals child, sorry. Then we're going to come underneath this and we'll say else. We'll open up the brackets. We'll say parent dot right equals child. Boom. Then we need to save or update both nodes in the dictionary. So we could come underneath this right here and we can say nodes square bracket parent val. Come outside of that, say equals parent. Then we'll come underneath that, we'll say nodes square bracket child val. Come outside of that, we'll say equals child. Then we need to record that this value appears as a child, so we'll come underneath this and we'll say children dot insert, open of the parentheses, pass in child val. Boom. Then we need to find the root node, and so every node except the root appears as a child exactly once. Therefore, the root is the only node whose value is not present in the children set. Like what I just was showing you with the with this 50 and the 1. Boom. So to do that, we're gonna say for, open up the parentheses, val, comma, node, come outside of that. And nodes, we'll open up the brackets. We'll say if exclamation point children dot contains, open up the parentheses, passing val. We'll come outside that. We'll open up the brackets and we'll return node. Otherwise, we'll return nil if no valid root was found by coming right underneath this, and we could just say return nil, y'all. Boom, that's all she wrote. Let's go ahead and give it a run. Make sure it runs properly, and it did not. So let's see what's going on. Can I find description? Oh, should have an S. Boom, let's run it again. See if that did the trick. It's accepted, so let's go ahead and submit it. Make sure it's still accepted after we submit it, because we all know how LeetCode can be. And look at that, y'all. 71 milliseconds beats 100% of users. That's what I'm talking about. That's what I like to see, y'all. So before we go, make sure you get one more look at the code. This is the top part. This is the bottom part, y'all. And yeah, with that being said, I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.